Okay, so we want to talk a little bit about vectors. And I have here points 2, 3, 5, 5 in the plane. Now, vector has a more general definition than what we're going to give it here, but we'll start with a very concrete definition in 2 dimensions, and then we'll build to see how you could do it in 38 dimensions if you wanted to. You can't draw it. Your best drawing you can do is some depiction of 3 dimensions. Since we live in 3 dimensions, we can't visualize a 4th dimension. But we can still do vectors in 4 dimensions or any number of dimensions. Okay, so we got the point 2, 3 and the point 5, 5. A vector from 2, 3 to 5, 5 is represented by an arrow so the 2, 3 is the initial point, 5, 5 is the terminal point. Okay? Now this vector moves this point 3 units to the right and 2 units up. Okay? So I can depict that motion by a sum of 2 vectors. Okay? This vector and this vector. Okay? So if I call this vector V, then this vector is in the y direction. So we're going to call this Vy, and then it's easy to see that we better call this Vx. And we can say that V equals Vx plus Vy. Make sense? Because you put these arrows together, head to tail, these 2 vectors head to tail, and then give you this vector. Because if you move from here to here and then from here to here, it moves this point exactly the same as this vector V. So it has exactly the same effect. Okay? Now this vector V can be applied to any point in the plane. Well, we'll get to that in a minute. Okay. I'm going to use order pair notation. Now, Vy is 2 units in the y direction, right? And Vx is 3 units in the x direction. 2 units in the y direction, I'm going to depict a vector that's 2 units in the y direction by an ordered pair with an arrow over the top of it. It means that this is a vector that moves you, and I always get these things backwards. You've got to watch me. I'll do this kind of thing. Okay? So that was wrong. It's 0, 2 up. But I'm talking about the y direction because that's the first one I did. Okay, well, anyhow, whatever I did, we'll correct it here. Okay, Vx is 3 in the x direction, 0 in the y direction, right? Sorry if I confused you, but that's how we're going to depict it. That's your Vx. And Vy is 0, 2. Okay? Now I can draw the vector V here without an initial point and a terminal point. I'm just drawing the vector V. This vector can apply to any point in the plane. It's often said you can move it anywhere. It's not confined to the points 2, 3, and 5, 5. Now that we've defined it, so here's your vector V, which is equal to 3, 0, vector 3, 0 plus a vector 0, 2. We know then that this vector is the sum of these vectors. Vx and Vy, so that this distance here is 2 and this distance is 3. Okay, so this is 2 units. I'm going to just draw the triangle. Okay, so we've got a triangle here. First of all, this is a right triangle. Why is it a right triangle? Well, because you can't say because this is a right angle. Because the y in the x direction, I did it again. Okay, keep an eye on me. You call me on that. You're not allowed to say anything, but you get up and wave your hands and throw things and whatever it takes. Okay. So this is your Vy. This is your Vx. Okay. Now, if you draw the triangle and just label the lengths of the sides, you get 2 and 3 here, right? So what's the length of this side? The hypotenuse. Okay? Well, it's the square root of 13, isn't it? And just in case you're asking the Pythagorean theorem, just square root of 2 squared plus 3 squared. Okay. Okay, so the vector has this length. So we say that the magnitude of V is equal to the square root of the magnitude of Vx squared plus the magnitude of Vy squared. The absolute value signs indicate how long the vector is. It's called the magnitude of the vector. Okay, well, one way to represent a vector is as a sum of x and y components. Okay? Another way to represent it is by its magnitude or length and its angle. The angle is always measured with respect to the direction of the positive x-axis, the positive x direction. So now we've got an angle here. Which I'll call theta. Can you tell me what theta is? Well, might be a little rusty in your trigonometry. We've changed the engineering curriculum around, so second-year engineering students used to have had statics when they came in here, so I didn't have to explain anything about angles and stuff. But not all engineering students now are taking statics because it's not relevant to electrical engineering, let's say. Okay? And so that was a good change. I don't always agree with the changes, but nobody asks me, so it doesn't matter. Okay? But, okay, there's theta. Now let me just observe the way I've drawn the picture. That theta is also up here. If you remember anything about geometry, what you have is a traversal of two parallel lines here, alternate interior angles, right? Okay. Theta is the inverse tangent of this side over this side. Okay? Tangent is the opposite side over the adjacent side, right? And this is the side opposite, this is the side adjacent to the angle. So theta is the inverse tangent of the magnitude of Vy, which is the length of the Vy vector, which is V2, divided by the length of Vx. Okay? I don't have room to write a better statement, and it might confuse if I did. So if Vx is less than 0, now Vx really stands for the magnitude of Vx, so this is an abuse of notation. But sometimes we abuse notation so we don't have to make a convoluted, confusing statement. And this just means if the x component goes in the negative x direction, in other words, this is a -3, okay? Your angle wouldn't be the inverse tangent of this, okay? So if you're back here in this direction, the inverse tangent actually something wrong with the way I did this. But the inverse tangent would just give you an angle. I'm going to have to change this. Okay. I'm going to have to take the magnitude signs away from this. Otherwise, I'm going to have too many cases. Okay, I'm just going to call this Vy over Vx, where right now Vy could be negative. Okay, if this was 0, -2, then Vy would be negative, be down this direction. That could be in this direction, okay? So with that convention, it's the inverse tangent of this. You've got to add 180 degrees if Vx is less than 0. Okay? Because you can't distinguish between Vy being positive and Vx being negative, which puts the thing in this direction, this direction, or Vy being negative and Vx being positive, which puts it in this direction. You would get the same arctangent because the arctangent only goes from negative 90 degrees to positive 90 degrees, or negative pi radians to positive pi radians, pi over 2 radians in both cases. Okay? So, since the inverse tangent doesn't distinguish between a vector in this direction and a vector in this direction, you got to do this. Now that's the simplest definition I can give you. Okay, when you look at it in the textbook, you'll see a slightly different definition, but it's totally equivalent. Okay, so your vector can be defined by this, a Vx and a Vy in coordinates, or by its magnitude, square root of 13 in this case, and its angle, the arctangent of Vy over Vx, which is, in this case, maybe about 0.7 or 0.8. Calculate the arctangent of 2/3. Okay? Okay, so sorry for that little bit of confusion, but there is the definition of vector in 2 dimensions. And the vector can be applied to any point. So if you apply V to the initial point, -7, 15, you're going to add 3 to the x-coordinate and 2 to the y-coordinate, because that's what the vector does. That's not 8. How did I get 8? It's a mystery. Something went haywire. Anyhow, negative 417. Okay? And that makes sense if you put this in a coordinate system here. It's going to have to use a slightly different scale. But negative 7, well, let's just say here's negative 7, 15. This vector moves you 3 to the right and 2 up. And it puts you at negative 4, 17. And if you sketch that out, it makes perfectly good sense. Okay? So, that's what a vector is in 2 dimensions. First definition. Now there's other definitions, so we'll go on to that.